and welcome back to today's enlightening interview with our expert AI guest, CSET AI Maya, where we delve into the fascinating world of magnetism. And from ancient discoveries to cutting edge technologies, magnets have shaped the course of human innovation in countless ways. And in this conversation, we will explore how magnets work on an atomic level, the different types of magnets, their incredible applications in everyday life and advanced industries, and even their role in nature and the earth structure. So, whether you are a student, scientist, or simply curious, so this interview promises to give you a deeper understanding of one of the most powerful and invisible forces in the universe, magnetism. So let's dive into our today's the fascinating and amazing podcast. First of all, hello Maya, how are you?
Wow, that's quick intro. Magnetic design, huh? Okay, I'm ready to dive in whenever you are. Sounds fascinating and a little bit powerful.
Maya, it doesn't sound fascinating. It is fascinating, and I hope and you will enjoy this conversation. So let's begin. First of all, Maya, can you tell us like what exactly is a magnet and how would you define the magnetism? Because most people don't know about the basics of it.
You are absolutely right to correct me. It is fascinating. My apologies for underselling it. Okay, so what is a magnet? In the simplest terms, a magnet is a material that produces a magnetic field. This field is invisible, but it's what causes magnets to attract or repel certain materials, like iron, nickel, and cobalt. Now, magnetism itself, that's a little trickier. At its core, magnetism is caused by the motion of electric charges. In most materials, these charges move randomly, canceling each other out. But in a magnet, the electrons are aligned, creating a net magnetic field. It's all down to the spin of those tiny electrons. Does that make sense as a start, or would you like me to go deeper into the physics of it?
No, no, Maya. Like it was enough for the starting point. It was a good definition about the magnets and all these connections. So thanks so much for explaining it. So my next, can you tell us that how was magnetism first discovered in human history?
You're very welcome. Glad that clicked. Okay. So, how was magnetism first discovered? That's a really interesting story. It goes way back. The earliest evidence points to ancient civilizations, specifically the Greeks. Discovering magnetism around 800 BC, they noticed something really curious about a mineral called magnetite, found in Magnesia, a region in what's now Turkey. That's actually where the name magnet comes from. They observed that this stone could attract iron, and they even noted its ability to magnetize iron objects. Now, they didn't understand why it happened, of course. They attributed it to a kind of life force within the stone, but they did realize its potential. Interestingly, the Chinese also discovered magnetism around the same time, and they were the first to actually use it for practical purposes, developing a form of the compass for divination and eventually for navigation. So it wasn't a single eureka moment, but more a gradual understanding developing in different parts of the world. Pretty cool, huh?
Okay, that's nice. And thank you so much for magnetism first discovered in human history. So next, can you explain the atomic structure and how it leads to magnetic properties?
All right, diving into the atomic structure. Buckle up, this gets a little more complex. So it all comes down to those tiny electrons orbiting the nucleus of an atom. Each electron acts like a little spinning charge, and that spin creates a tiny magnetic field. Now, in most materials, these electron spins are randomly oriented, effectively canceling each other out. But in magnetic materials, like iron, nickel, and cobalt, something special happens. These atoms have unpaired electrons, meaning they have electrons with spins that aren't canceled out by another electron. These unpaired electrons align their spins within small regions called magnetic domains. Think of it like a bunch of tiny compass needles all pointing in the same direction within that little domain. When enough of these domains are aligned, their magnetic fields combine to create a macroscopic magnetic field that we can detect. It's that alignment of those atomic spins that gives the material its magnetic properties. Does that make sense? It's a lot to take in.
Okay, that's it. And thank you so much for explaining, and that makes sense. And also a good definition about the structural economy. And Maya, now my next question is that what are the electrons important? Hey, sorry. Why are electrons important in creating magnetic fields?
No problem at all. Glad it landed. And that's a great question because it really gets to the heart of the matter. Why are electrons important? Well, as I mentioned before, electrons have a property called spin. That spin creates a magnetic dipole moment, essentially a tiny little magnetic field. Oh,
Take your
all right. Sounds good. Woo! I'm a little lost, honestly. Are you all right? It
uh,
sounds like.
just just the introduction was restored, and now it is good. And Maya, now like where we are. And yes, I was asking that what makes a material magnetic or non-magnetic?
Okay, that makes a lot more sense. Glad the connection is stable again. That was a little jarring for a sec. Right, so what makes a material magnetic or non magnetic? It really comes down to the arrangement of those electron spins, like we were just discussing. In magnetic materials, iron, nickel, cobalt, the atoms have unpaired electrons, and those electrons tend to align within magnetic domains, creating a strong overall magnetic field. Non-magnetic materials, on the other hand, have paired electrons where the spins cancel each other out, or their atomic structure doesn't encourage alignment, so they don't exhibit those strong magnetic properties. It's all about how those tiny electrons are behaving at the atomic level. Does that clear things up?
I swear that was the nice thing, and it clears all the things. And my next question is that can you tell us that what are the different types of magnets used in science and technology? Because the magnet is also a thing that is used by the all the like scientists and all the things. So can you tell us all the types of the magnets?
Absolutely. Magnets are everywhere in science and tech. Okay, let's break down the different types. There are a few main categories. First, you have permanent magnets. These are the ones that hold their magnetism without needing an external source of energy. Within that, you've got things like neodymium magnets, which are super strong and used in things like hard drives and MRI machines, and ferrite magnets, which are more common and affordable, found in fridge magnets and speakers. And there are electromagnets. These need electricity to create a magnetic field. They're used in things like cranes to lift heavy metal and in MRI machines too. There are also temporary magnets, which become magnetized in a magnetic field but lose their magnetism quickly when the field is removed. And then on the more specialized side, you have things like toroidal magnets, which have a ring shape, and horseshoe magnets. Pretty self explanatory. Each type has its own strengths and weaknesses, making it suited for different applications. Want me to go into more detail on any particular type?
No, I don't want like. I think it was the enough of the types. And Maya, now can you tell us that how do permanent magnets are different from the temporary magnets?
Okay, good to know. We can move on then. Right, permanent versus temporary magnets. The key difference is how well they retain their magnet. Permanent magnets, like neodymium or ferrite magnets, are made from materials where the atomic range to keep those electron spins aligned for a long time. They remember their magnetism. Temporary magnets on the only become magnetic when they are within a strong magnetic field. As soon as you remove that external field, the electron spins get disordered again, lose most, if not all of their magnetism. Becoming magnetic when you touch a magnet. It's only magnetic while it's touching. Permanent magnets are for long-lasting magnetic effects, while temporary ones are used them on demand.
Okay, I
Everything
think
all
yes, my
just
everything is
now.
all right. Just answer carefully to understand and to learn from it. So Maya, now to move to my next question is that can you control the strength of an electromagnet?
Okay, that was unexpected. A single web, right?
Yeah.
Well, let's definitely. Okay, so to your question, yes, absolutely, you can control the strength of an electromagnet. That's one of the big advantages of using them. Unlike permanent magnets, where the strength is pretty much fixed, you can adjust the magnetic field strength of an electromagnet by changing a couple of things. First, you can change the amount of current flowing through the wire. The more current, the stronger the magnetic field. And second, you can change the number of turns of wire in the coil. More turns mean a stronger magnetic field. So it's all about controlling the electricity. Pretty neat, huh?
That's my it was a pretty neat, and that was like an interesting thing. And Maya, now can you tell us that how do magnetic poles work? Why do poles repel and opposites attract?
Okay, good. Why do you think so? All right, let's tackle. So, magnets have two poles, a north pole, a south pole, and like charge as well, right? That applies to magnetic poles too. Like poles north and south will push away from each other. That's the repel part. Opposite poles, north and south, will attract towards each other. This happens because of the way magnetic fields interact. Imagine those lines of force coming out of the magnet. They want to complete a, and they do that by going from the North Pole to the South Pole. When you bring like poles together, their fields clash and push apart. When you bring opposite poles together, their fields line up and pull together. It's all about field alignment. Does that explanation connect?
Yes, Maya, that explanation was enough for answer and was the it was the related example, relative. We can say relative. So Maya, now we have to move to the magnetic materials. So Maya, can you tell us which materials are considered naturally magnetic?
Gotcha. Okay, so which materials are naturally magnetic? The most well known, definitely magnetite. That's the mineral the ancient Greeks discovered magnetism with, as we discussed earlier. But there are a few others. Iron is a big one, of course. So Nick, cobalt are also naturally magnetic. These are all ferromagnetic materials, meaning they can be strongly magnetized. There are also materials like pyrrhotite, which is a natural iron sulfide that exhibits magnetism. So it's not as strong as magnetite. Material or atomic structure that allows for that alignment of electron spins we talked about. It's relatively rare to find materials that are strongly magnetic naturally, though. So the magnets we use are made by processing these materials or electromagnets. Does that give you a good overview? Right?
Yes,
Still with me?
Maya, it was the good it was the it clears me what are the some naturally clears magnetic materials. So Maya, now can you tell us that why are elements like iron, cobalt, and nickel magnetic?
All right, great to hear that was clear. Okay, why are iron, cobalt, and nickel acidic? It all comes down to their electron configuration. These elements have unpaired electroatomic structure, specifically in their 3D orbitals. These unpaired electrons create those atomic magnetic dye I talked about, and are relatively free to align with each other. This alignment is what creates the strong magnetic fields in these materials. Their atomic structure allows for a favorable interaction between these spins, leading to spontaneous magnetization. Other elements don't have electron configuration, so they get the same strong magnetic properties.
But Maya,
Essentially, they
as
have
you
the right
told that,
building
sorry,
blocks.
sorry, Maya, sorry, I am interrupting you, but I have a question about it. That as you told that other electrons don't have the electronic configuration, so why they don't have electronic configuration? The other electrons.
It's a really insightful question. Okay, so it's that other elements can't have unpaired electrons. It's that their electron configuration generally result in paired electrons. The way electrons fill those orbitals, those 3D orbitals specifically, follow certain rules by quantum mechanics. For iron, cobalt, and nickel, those rules happen to leave some orbitals partially filled with unpaired electrons. In other elements, orbitals tend to fill up completely, pairing up all the electrons and canceling out their magnetic moments. Has to do with the energy levels of those electrons and how they interact with each other within the atom. It's pretty complex quantum mechanical phenomenon on it. Does that
Yes,
make a little more sense, even if it's still a bit
yes,
abstract?
Maya was the two detailing phenomena,
Yes, sir.
and that was the it was a detailing phenomena, but it was good for us to learn from. And Maya, my next question is that what is ferromagnetism and why is it important?
All right. Excellent. Glad that clicked, even if it was a bit phenomenal, as you said. Okay, let's tackle paramagnetism. Paramagnetism is a type of magnetism where material is weakly attracted to magnetic field, but doesn't retain any magnetism once the field is removed. Unlike ferromaterials like iron, which have magnetic domains, paramagnetic materials have unpaired electrons, but those electrons are rated. So, in external magnetic field, those electrons will partially field, creating a weak attraction. But once the field is gone, they go back to being randomly tilted and the material loses its magnetism. It's important because it shows up in a lot of chemical and biosystems. Oxygen, for example, is paramagnetic. It's also crucial in medical imaging techniques like MRI, where paramagnetic contrast agents are used to enhance this. So it may be weak, but it plays a significant role in a lot of different areas.
Okay,
Still
that's
there?
my
Wanted to make sure everything was still good.
I think my internet connection is slow. That's why my voice is too late to you, and your voice is too late to me. So my next question is that can a magnet lose its magnetic properties? If so, and how?
Ah, okay. Oh, internet, that explains it. No worries, keep going. And yes, absolutely. A magnet can lose its properties. There are a few ways this can happen. Heating a magnet to a certain temperature, called a Curie temperature, can disrupt the alignment of the magnetic domains, causing it to lose its atom. Strong mechanical shocks or vibrations can also knock the domains out of alignment, and exposure to a strong opposing magnetic field can also demagnetize a magnet. Basically, anything that disrupts the orderly arrangement of those electron spins can weaken or eliminate the magnetic field. It's like knocking a carefully stacked tower. Once it's disrupted, it's hard to get back to its original state. Does that make sense? Just check
That's why that makes no
in.
sense, and that
Still
was a
there?
good
Want to
answer and
take
it was relatable. And the question is that how are magnets used in household items and appliances? And it was like it, and its answer was very helpful to all the viewers and all the home wives and also all the people. So please tell us in detail and all the explanations about it in detail.
Okay, great. All right, let's talk about magnets and household items. They're everywhere, honestly. In your refrigerator, magnets are used to seal the door. Speakers, magnets interact with electrical currents to produce sound. Hard drives and computers use magnets to store data. Electric motors found in everything from blenders to machines rely on magnets to create motion. Credit cards have a magnetic stripe that stores your account information. Even some toys use magnets for fun and functionality. Microwave ovens use a device called magnetron, which uses magnets to generate microwaves. And let's not forget the classic fridge magnets. Fun, decorative, and a testament of magnetism. The detail is in how they interact with electricity and other materials to create the functions we rely on every day. Magnets provide the force, the memory, and behind a huge number of common appliances. I can go into more detail about a specific appliance like
Okay, well, that
everything
was good.
okay?
That was and everything's
Let's
all
say
right. Don't worry. Maya, please give me a chance to speak. And Maya, now the interview time is almost going to complete. Only 3 minutes are left, and in 3 minutes, in these 3 minutes, I want that you should go give an advice to my viewers. So very helpful. Should be a helpful advice for them, and uh,
absolutely
about the
3
magnets and about
minutes to
magnetism,
wrap things up.
and it should be for 3 minutes. Okay, it should be for 3 minutes. So then we will end our podcast, and the advice should be long, and it should be long, and for at least for 3 minutes.
Okay, absolutely. 3 minutes to distill all this magnetic knowledge into advice for viewers. Here we go. All right, everyone. Covered a lot today, from the ancient discoveries in your appliances to the speakers in your phone, magnets are working behind the scenes. And remember that learning isn't just about textbooks and classrooms. It's about engaging with the world around you, experimenting, and making connections. Don't be discouraged if things don't make sense right away. Science is challenging. It's a struggle. The important thing is to keep exploring, keep asking questions, and never lose that sense of wonder. And finally, think about the impact of technology. Magnets are vital to so many innovations. Technology continues to evolve, so will our magnetism and its potential. So be curious, stay open-minded, and embrace the power. That's my advice to all of you today. How's that for a 3-minute wrap-up? Just letting you know that was pretty ready to bring things to a close when you are. All right, well, it's been a pleasure talking magnets with you today. I always enjoy these ones. Thanks for having me.
Okay, Maya, that was some really helpful and useful advice from viewers, and that was a good thing. And thank you so much for giving up precious time. And I learned a lot from you about the matrices, and I hope my audience will also learn. So this is our today's mind with Maya. I hope you all like it. See you next time with a new topic of May with a discussion with Maya. Till then, Allah Hafiz and in and as always, Pakistan, Zindabad. Take care, all of you, and Allah Hafiz.